Hey guys, Mr. Backward here. In this video, we're going to look at linear approximation. So because the derivative is defined as the limit of the ratio of the change in the output to the change in the input, so dy dx is the limit of the change in y over the change in x as the change in x gets really close to 0, we can then approximate the derivative by finding the change in y over the change in x when the change in x is very small. This also works the other way. Very often it's going to be easy for us to calculate the derivative, which we can then use to help us approximate the change in the y value when the change in the x value is known. So what's happening there is that very close to the point where we are calculating the derivative, the graph of the function is very close to a straight line. So we can say that the curve is locally linear, which means as we zoom in on the picture, it looks like a straight line. And specifically, it looks like the tangent line. So if we were looking at this curve, y equals f of x, and we were looking at finding a tangent line at the point a comma f of a, well, we know that the slope of the line is the derivative, and then using this point a and f of a, we can really do some point slope things. Remember, point slope form looks like y minus y1 equals m times x minus x1. Well, if we use the a and f of a as our x1 and our y1, and we use the derivative as our slope, then this equation would say y minus f of a equals the derivative of f at a times x minus a. And then if we wanted to get y alone, I would add this f of a over to the other side. So then we can say that y is equal to f of a plus f prime of a times x minus a. And this is actually called linearization. So if f is differentiable at x equals a, then the equation of the tangent line, this is that linearization that we just looked at. So we can call it L of x, that's equal to f of a plus f prime of a times x minus a. That's called the linearization of f at a. And then the approximation f of x is approximately equal to this linearization at x. That's called the standard linear approximation of f at a. And then that point x equals a is called the center of the approximation. So here's what we're going to do. We're going to find the linearization of f of x equals the square root of 1 plus x at an x value of 0. And then we're going to use it to help us approximate the square root of 1.02 without using a calculator. But then after we approximate that value, then we will use our calculator to help us determine how accurate our approximation was. So we've got ourselves an x value. We're going to need a y value. So we're going to take that x and we're going to plug it into our original function. So if we do that, if we plug in 0, well, 1 plus 0 is 1, and the square root of 1 is 1. So we get the point 0, 1. Now the next thing we're going to need is the derivative of this f of x function. So what I would do is I would take that square root and I would write it as a 1/2 power. So I would write it as 1 plus x raised to the 1/2 power. So then what we would do is drop that 1/2 power down, subtract 1 from the power using the power rule, and that's a negative 1/2. Technically, we should do the chain rule, but the derivative of the inside stuff would just be 1, so we don't really need to attach a times 1 there. But then we want to find the slope specifically at this x value of 0, so then I would plug in 0 for the x in the derivative, and when we do that, we would get a slope of 1/2. So here's all the information that we're going to need. This x value of 0 is our a value, and then this 1 is our f of a value. The derivative at 0 gave us the slope that we're going to need, so now we should be able to write out the linearization. So that linearization function L of x was equal to f of a plus f prime of a times x minus a. So our f of a is 1 plus the f prime of a. So the derivative of f at a was that slope 1/2 that we got earlier, and then x minus the a value of 0. So if we simplify this down, then it's going to be 1 plus 1/2 x. That is our linearization function. Now, if we want to approximate what the square root of 1.02 is, then what we're looking at is underneath that radical, it's really like having 1 plus 0.02. So the x value for this function that we're looking at is this 0.02. So we're going to take this linearization function that we just got, and we're going to use that x value of 0.02. So we're going to do our linearization at 0.02, which means we're going to take 1 plus 1/2 times 0.02. Well, half of 0.02 is 0.01, so we can add those together and get 1.01. So that's our approximation for the square root of 1.02 using our linearization. Now we said we wanted to check our answer on our calculator, so if we go with the square root of 1.02 and hit enter, we get 1.00995. So doing a little rounding, that double 9 in there is going to bump the 0 up to a 1. So we can see that our approximation was super close to what the actual value was because we were using an x value that was very, very small, an x value of 0.02. But as our x values get further and further away from 0, we're going to lose accuracy on our approximation, and it's going to be less and less useful the further away we get from that x value of 0. Taking a look at this example, we're doing more linearization, but now we're using some trig. So the function we want to look at is the cosine of x at an x value of pi over 2, and we want to use the linearization there to approximate the cosine of 1.75 without using a calculator. And then just like we did on the last one, after we get our approximation, we will use our calculator to help us determine how accurate that approximation was. So the first thing we need to build is our ordered pair. We were given an x value of pi over 2, so I want to plug that into the original function cosine of x so that I can get that y value. Well, if I plug in the pi over 2 there, then we're doing the cosine of pi over 2, and using a unit circle, the cosine of pi over 2 is 0. Now the next thing we need to do is find the derivative of this cosine function, and the derivative of cosine is negative sine of x. But then to specifically find the slope at the x value of pi over 2, we would want to plug that into our derivative that we just got here. So the sine of pi over 2 is 1, but if we attach a negative to that, then we get a slope of negative 1. So this pi over 2 is our a, this 0 is our f of a, and then our slope is the derivative at a. So our linearization function says take the f of a, but then add on the slope that we just got times x minus the a value of pi over 2. So if we go through and simplify that down, then we get our linearization function to be negative x plus pi over 2. Now remember, we want to use this linearization to approximate the cosine of 1.75. So we're going to do the linearization at 1.75. So we're going to take that 1.75 and plug it in for our x in here. So this is going to say negative 1.75 plus pi over 2. Now if I were to get a decimal approximation there, this is going to be approximately negative 0.1792 if we round that off to 4 decimals. Now going to our calculator so that we can figure out what the actual value is. Because we're going to be doing some trig, the very first thing that I want to check is that my calculator is in radian mode, and it is. So I'm going to do the cosine of 1.75. So we get an answer of negative 0.1782. Well, the approximation that we got was negative 0.1792. So again, we can see that our approximation is fairly accurate, maybe not quite as accurate as our previous example, but still, we're pretty close. Now that first example that we went through actually introduced a special case of a general linearization formula that's going to apply to powers of 1 plus x for small values of x, and that approximation is if we have 1 plus x being raised to some k value power, then the approximation that we're going to end up with in there is 1 plus k times x. Now, if that k value is a positive integer, then it follows from the binomial theorem, but the formula is actually going to hold true for all real values of k. So we're going to use this formula to find polynomials that will approximate the following functions for some values of x that are really close to 0. And the first one that we're going to look at is the cube root of 1 minus x. Now we said that this formula was going to work for powers of k on this 1 plus x. So what we're going to have to do is rewrite this cube root as a power. And a cube root is the same thing as a 1/3 power. So we can write this as 1 minus x to the 1/3 power. Now our formula technically says 1 plus x. I can change this to say 1 plus negative x, all being raised to the 1/3 power. And now it's set up how I need it to be in order to use this approximation formula. So then this would approximate into being 1 plus the k value is the power. So that's going to be 1/3 times the x, but in here we've actually got a negative x. So then this will actually be 1 minus 1/3 x. So this will be our approximation for x values that are small. Now same thing, but changing up the function that we're working with. Now we've got this 1 over 1 minus x. Again, we were talking about powers of 1 plus x. So the first thing I'm going to do is convert this into a power. So if we take this 1 minus x and bump it up to the top of the fraction, then it's really going to be 1 minus x to the negative first power. But then we want it to look like 1 plus x. So I'm going to call this 1 plus negative x raised to the negative first power. And now we can use our approximation formula. So this will be 1 plus the power k, which is negative 1, times the x, which is actually a negative x. So then if I do the negative 1 times the negative x, well then this just turns into 1 plus x. So this is going to be our approximation of this function, again, for x values that are small. Similar type of problem, but again, changing up the function that we're working with. So now we've got the square root of 1 plus 5x raised to the 4th power. Again, we want powers, so I'm going to take this square root and turn it into a 1/2 power. So this is going to be 1 plus 5x to the 4th raised to the 1/2 power. Now this time, the x that we're dealing with is really this whole 5x to the 4th. So if I use this approximation formula, then it's going to be 1 plus the 1/2 power times the whole 5x raised to the 4th power. Well, with this 1/2 times this 5x to the 4th, I could really write that as 1 plus 5/2 x to the 4th power. So this will be our approximation this time. And then one more like this that we're going to take a look at. Now we've got 1 over the square root of 1 minus x squared. Again, we want to get this written as a power so that we can use this approximation formula. So the first thing I notice is that we have that square root on the bottom. So I'm going to turn that into a 1/2 power. So this will be 1 minus x squared raised to the 1/2 power on the bottom of that fraction. But then I want to bump that up to the top by making that power negative. So this is going to be 1 minus x squared to the negative 1/2 power. But again, we want it to be 1 plus x. So I'm going to write this as 1 plus negative x squared raised to the negative 1/2 power. And then if I use my approximation formula, it's 1 plus the power, so negative 1/2, times the x value, which is negative x squared. Now in here, that double negative will turn positive, so this will be 1 plus 1/2 x squared as our approximation. Now the last thing we're going to do is use linear approximation to help us approximate some roots. So in this first one, we're going to approximate the square root of 123. Now because we're doing a square root, then we're going to let our f of x function just be the square root of x. Now as we're looking at 123, we know that that itself is not a perfect square, but we do have a perfect square that's pretty close to 123. So what we're going to do is actually look at an x value of 121 because that's the closest perfect square to 123. So we're going to center our linearization at 121. Now, if we think about making a point using this x value of 121, well, if I plugged that into my square root function, then I would get an answer of 11. So the 121 is going to be our a, the 11 is going to be our f of a. Now, we still need to find the derivative of this f of x function. So finding the derivative of that square root function, I would think about it as x to the 1/2 power. So this is going to be 1/2 times x to the negative 1/2 power. But then we don't typically like negative powers, so I can write this as 1/2 times 1 over the square root of x. Now we're looking specifically at an x value of 121, so if we plug that in here, then we'd get 1/2 times 1 over the square root of 121. But we know that the square root of 121 is just 11, so if we do 1/2 times 1 over 11, then we're going to get 1 over 22. Now that's going to be the slope that we're going to use as we write out our linearization. So our linearization function is L of x equals the f of a, so 11, plus the slope that we just got, so 1 over 22 times x minus the a value of 121. Now we want to approximate the square root of 123, so we're going to use an x value of 123. So then our linearization at 123 is 11 plus 1 over 22 times 123 minus 121. Now if we were to go ahead and type all of that into our calculator, we'd get 11.09, and that 0.09 keeps repeating. And then the last example that we're going to look at is using some linear approximation to help us approximate the cube root of 123. So again, we're going to need a function, and because we're doing a cube root, let's let our f of x function just be the cube root of x. Now the closest perfect cube to 123 is an x value of 125. So if we build our ordered pair, we've got 125 as the x value. The cube root of 125 is just 5. So this is our a, this is our f of a. Now we need to go through and find the derivative of this cube root function. So if we think about this as x to the 1/3 power, then as we find the derivative in here, using the power rule, this is going to be 1/3 times x to the negative 2/3 power. Now I'm going to drop that down to the bottom of a fraction so that we don't have the negative power. So I'm going to write it as 1/3 times 1 over x to the 2/3 power. Now because we're dealing with an x value or an a value of 125, if we were to plug that in here for our x and simplify things down, we would end up with our slope being 1 over 75. So then our linearization function is 5 plus that 1 over 75 times x minus the 125. Now going back to the start, we wanted to look at the cube root of 123, so we're going to do our linearization at 123. So 5 plus 1 over 75 times 123 minus 125. Typing all of that into our calculator, we'd get 4.973, and the 3 keeps repeating. Now, if we were to go through and actually use our calculator to help us find the actual values for part A and part B, we would see that the actual values are really close to our approximations. That's going to be it for this video. Thanks for watching.